Hi PGW students, will hopefully be a short video where we wrap up the lecture on phylogenetic trees. So the first part we're going to be looking at how we determine whether a shared trait is due to common ancestry or often convergence, and we'll be spending a lot of time on this later in the semester, and we'll be coming back to this. And there's some unusual language here and some terms we'll kind of define, but again, it won't be that terribly important. The last two slides where we look at the phylogeny and evolution of venom delivery systems and toxins in snakes, I'm going to have we'll have an iClicker question at the beginning of class, so I guess pay most attention to this. So as we look at this first slide, what we're looking at here is we have let's just say three species, 1, 2, and 3, and 1 and 2 both have dark coloration. So as you look at this, we start at the base of the tree in the ancestral node, and 1 and 2 have dark coloration, and 3 has light coloration. What we would say here is this particular trait, in terms of brown coloration or darker coloration, the fact that it's shared between 1 and 2, you could argue that this evolution of dark coloration arose in the ancestor to the 2, and this is what we call a shared character between these two species due to common ancestry. The other fancy term is to call that a synapomorphy, and probably on your flip cards on Moodle, synapomorphy will probably be defined as a shared character due to common ancestry. It's often called a shared derived character, meaning it's gone from the ancestral state to a new state or derived. Now, there are also other ways that you could map this coloration onto the tree depending on what the phylogenetic relationship is among these three species. So let's look at two other alternatives here. Now we have, instead of 1 and 2 being grouped together, we have 2 and 3 as sister taxa, and 1 falls outside of it. And we have the same tree on both the left side and the right side. So in this particular case, the way we've mapped this character state change on here, we're basically saying the orange coloration is ancestral, and dark coloration rose in the lineage leading to species 1, and it also arose in the lineage leading to species 2, but they arose independently. This is what we call homoplasy. It's kind of like analogy, but these character states, the dark coloration is shared in common, not due to common ancestry, but you could argue due to convergent evolution or analogy. And this is what we often call, when shared characteristics are due to analogy or convergent evolution, that's a homoplasy. Again, I'm not too worried that you understand all this. Here's an alternative here. You could also map this state in the character change where you had dark coloration is in the ancestral group, and this is what we call, and then dark coloration is what's called a symplesiomorphy, in that 1 and 2 share this in common because they inherited it from a deep ancestral node, or an ancestral, it's called a shared ancestral characteristic. And then the yellow coloration arose on this lineage leading to 3. Okay, so those are just kind of the different ways you can map these traits and get it depending on how the species 1, 2, and 3 are depicted on a phylogenetic tree. Now let's go how we actually often resolve some of this and come to a better understanding of how characters evolve. And the way we do this is through what we call outgroups. And so what we have here is outgroup species 1 or outgroup or species 2. And we usually base that on choosing things that we know are sort of ancestral or outside the species that we're interested in looking at. So we're really not interested in determining the phylogenetic relationships. We use these outgroups to kind of what we call polarize the change in the evolutionary states of characters. Okay, so what we have here, we have outgroup species 1, outgroup species 2, and here's the common ancestor to all of them. Here's the common ancestor to outgroup species 2 and what we call species 1, 2, and 3, or the in-group. And what we have here again, as you go up this branch, you'll see it's not a completely resolved phylogeny. It's what we call a polytomy. So we don't necessarily know the relationships between 1, 2, and 3. So actually what we do is we use the state of the character in the outgroup to determine what is the best depiction of the phylogenetic relationships between species 1, 2, and 3. And we'll be talking a lot more about this. We usually go with what is the simplest model of evolution or most parsimonious. So let me give you an example. So here we have 1, 2, and 3 pointed out here. and here are the outgroups. In scenario A, what you're saying is the only time the character changed on this particular tree, it went from the ancestral character of yellow to the derived character state of brown in species 1 and 2. So it originated once, and this is what we call one tick mark or one step on the tree. In the other case where you had homoplasy, where 1 and 2 arose independently, what you've got here is the ancestral state is always yellow, but the brown coloration or darker coloration arose independently in species 1 and 2. So you have to mark 2 changes on this tree to get to the brown coloration leading to species 1 and species 2. The other possibility here is you could have the orange coloration and then the evolution of dark coloration or brown coloration at this point, and then what we call a reversal back to the ancestral state where 3 has the yellow. Again, so this is the origin of the novel trait and then a reversion back. This requires 2 steps too. The notion of parsimony is pretty simple. Out of these 3 scenarios, which is the simplest and requires the fewest number of changes, the argument would be that this particular tree, given this particular character, species 1 and species 2, have a shared common ancestor and those group together. And that's the best way to present this data. Okay, and we'll be spending a lot of time on that. Okay, the last thing, and this will be the focus of the iClicker question, is to look at these rather amazing group of advanced venom delivery systems. And this is an example from a viper. So viperids are notorious for the advanced delivery systems from a compressor muscle, obviously, that compresses a venom gland and then delivers the toxic venom from a primary venom duct through a secondary venom duct, through the special protective sheath, and then through the tooth, through the fang, and then the venom is released. And obviously this is a very important means of predation to immobilize their prey, and these are really rather complex systems. And so we'll come back to that slide. So here's a phylogeny of some of the major groups of snakes. And it's a fairly complicated one. I'm going to try to make it as fairly simple as possible. And there's a good discussion of this in your book, so if you want to go back and read it. The basic idea here is, again, what we're doing is we're mapping the origin of traits onto a tree. And what we see in this case is there are a group of snakes that include all of these species that have sort of specialized oral secretory glands, and they all have that. Then up on this branch, which includes all the viperids and all the cobras and rat snakes and all sorts of other things, they have sort of specialized dentition. And usually what this involves is sort of fangs and things like that that help to catch prey, immobilize prey, maybe through toxin delivery and all sorts of things. Okay. One of the things we want to focus on here are the advanced venom delivery system that we just showed in this particular case. And this is what we see here is a viper, and that group is right in here. So Texas copperheads, they're in this family, the Viperidae, a very toxic snake. And all of these various families of the Viperidae, Atractospididae, and the Elapidae all have these advanced delivery systems. And when everybody knew that and thought these advanced delivery systems were, obviously the mechanism by which these toxins are produced and how members of these families of snakes delivered their systems. So it was kind of assumed early on that, well, a lot of these things, they have fangs, but they don't really have these advanced delivery systems, so they must really not be delivering a lot of toxic chemicals to immobilize prey. And what this wants to show you is you don't necessarily need an advanced delivery system to deliver really toxic chemicals and to immobilize prey. And all we're really going to focus on here is that there's this thing called a 3-FTX toxin that is based on this phylogeny, and people started to explore where this toxin is found, and we'll give you just one example of this, that this 3-FTX toxin arose in this ancestor, and potentially a lot of these other things besides the Elapidae and Atractospididae from this thing, people suggested, well, maybe they do have toxins. Okay, so what I'm going to show you is an example. The rat snake is a fairly common snake. Nobody thought it had sort of toxic and it didn't have an advanced delivery system. They knew that it bit things, but they didn't really think it immobilized things very quickly. But it turns out that when you go in and look at and dissect out the sort of the secretory glands in here, and when they isolated it, they found this 3-FTX toxin that is found in all these other things, but they do it through a different delivery system. So what this suggests is, even though you don't have this advanced delivery system, it's only in these 3 things, many of these other species may have these toxins, but don't require these sort of advanced venom delivery systems to immobilize prey. And what people are now going in, they're looking at these other families outside of the Colubridae. They're looking at these other things, and what they're finding is what they thought were harmless snakes really weren't toxic snakes. Basically, they were just sort of catching prey in their mouth and eating them. It turns out a lot of these things are delivering this toxin through less specialized and advanced. They don't have these advanced delivery systems. So once again, this phylogeny can tell you a lot about how traits originate. It might lead you to ask other questions and realize that, well, maybe you didn't think these were capable of toxic delivery to immobilize prey, but it turns out a lot of them do. So what I will do at the beginning of class next week, we will have a sort of quick eye-clicker question at the beginning of class, sort of asking a question about this result. Okay, thanks.